first method that we're going to talk about is called probabilistic counting. So again, the problem we're talking about is cardinality estimation. It's a fundamental problem that has a lot of applications when memory is severely limited. And what we're going to ask is, instead of exactly how many different values are there, we're going to say about how many different values are there. And we'll precisely characterize what we mean by about later on. So there's various constraints in all these kinds of applications. So one thing we're going to insist is we only get to make one pass through the stream. That is, you only get to look at each data value once. When you get a data value, you don't get very much time with it. You think of a network switch or some other type of process where things are coming in so fast you only get a little time with it. We don't have very much memory because we have lots of streams, for example. And we still want to produce as accurate an estimate as we can. So we're trying to satisfy all these constraints in an algorithm to address this problem. And there's lots of applications. We just looked at how many unique visitors to my website. Actually, one of the original ones was a so-called join operation in a database. There's different ways to slice a database, and the efficiency of the operation depends on knowing how many different values there are in each slice. Maybe a bank or financial institution has a huge number of customers. They all have data streams, and they might be interested in how many different websites has each customer visited, or which ones are most and least popular. And there's also applications around our computational infrastructure, as I mentioned, like switches on the internet and similar types of applications. So just to fix ideas of the scope of the problem, to say what we need in order to be able to have an effective practical solution, we're going to think about, in modern applications, say billions of streams, each one having trillions of values. You have to be able to handle problems of that scope nowadays. But the algorithm that we're going to talk about was invented by Philippe Flageolet and a colleague in 1983. In those times, the numbers were much, much lower, but still relative to what we're able to compute, it was the same type of constraints. And as I mentioned, it was for database applications. So the contributions of this 1983 paper are, number one, they introduced the idea of trying to estimate cardinality in a big data stream using a small amount of memory. That's the idea of a streaming algorithm that gets one pass through a data stream and has to make sense of it. And the idea of a small amount of memory. We've got a lot of data and we have a very small sketch. But even more important, this paper has a very detailed analysis that gives tight bounds on the accuracy and full validation of the math and hypotheses derived from the math with experiments, which means that it's a practical algorithm that has remained effective for really a long time. We'll talk about a couple of refinements, and we'll go into this algorithm in quite a bit of detail. The bottom line is, and the reason that we're talking about it, is it's a great example of the effectiveness of the scientific approach to algorithm design. We'd like to do this, be able to do this for so many other problems, and that's why we work in continuing to develop new mathematical tools and to experiment with new algorithms. Okay, so first step for probabilistic counting is to use hashing. And so the idea is we're going to take the value, whatever it is, in our reference application it was long strings, and we're just going to transform it into a computer word, something that fits in, say, a 32 or 64-bit value. With very high probability, that's not going to affect the cardinality count 64-bit value. False collisions in the hashing are going to be extremely rare. And computing a hash function is something that's built in and readily available in modern systems since the beginning, really. And the reason we want to do this is that it allows use of fast machine code operations when we encounter each new thing in the data stream. Really, the most expensive thing is computing the hash function. In Flageolet, Martin original paper, they use 32 bits. Nowadays, we use 64 bits, which is lots of values. And maybe we could think about using 128 bits, but we'll use 64 for most examples. In Java, all data types implement a hash code method. Actually, we often override the default to try to make sure that we have a pretty good hash function. In our reference, the string data type, when it creates the thing, it computes and stores the value, so it's only computed once. So that's what you do to get a 32-bit value in Java, and I'm sure it'll be changed to 64 very soon. So the bottom line from this first step is that we're going to do cardinality estimation on binary integers. So these we can think of as a random stream of integers. That's going to be our first hypothesis. And they're random except if there's equal strings, they're going to hash to equal values. So the cardinality count is unaffected. That's the first step. So now we're going to be thinking about 32 or 64-bit values that fit in a computer word. And of course, as I mentioned, that means we're going to assume that the uniform hashing assumption is reasonable. And the implication of that is we're going to need to run experiments to validate any hypothesis that we might have about performance. But again, that's no problem for researchers in the analysis of algorithms, because we always validate hypotheses. Our end goal is the development of algorithms that are useful in practice, and it's the responsibility of the person designing the algorithm to validate that it's useful before claiming it. After decades of experience, discovering a performance problem due to hashing would really be a significant research result, and it has happened once or twice in history, but we're going to assume that uniform hashing is reasonable. And it's just a bedrock principle of research in the analysis of algorithms is that we experiment to validate hypotheses. That's what we do. Usually the experiments turn out okay, but you never know. That's why you do the experiment. Okay, so now that we have, we're working with values that fit in a machine word, we're going to work with two integer functions that are the basis for the probabilistic counting algorithm. First one, called little r of x, that's the number of trailing ones in the binary representation of x. Or another way to think of it is it's the position of the rightmost zero. And then related to that, capital R of x is 2 to the power little r of x. So here's an example. Here's a 16-bit value. Position of the right, if we number them from 0 from right to left, position of the rightmost one is number 1, so that's r of x, or the number of trailing ones is 1. And then capital R of x is 2 to that power, so in this case that's 2, and that's 1 0 in binary. If the rightmost 0 is at the end, then little r of x is 0, big R of x is 1, even in binary. Or a more typical case, there's 5 trailing ones, position of the rightmost 0 is 5, big R of x is 32, and in binary, you can see that it's take the trailing ones and turn them to 0, and take the 0, turn it to 1, forget about everything else. It's another way to see what big R and little r are. Okay, so these are functions that are going to play a role in our algorithm. Position of the rightmost 0, number of trailing ones, that's little r of x. Now, what bit whackers have known since the beginning, in the early days of computing, people like Flageolet and me and many others had to know about machine language programming, because that was the most efficient way to get things done often. And one thing that we learn is there's functions like this that are easy to compute, and this is a famous one. So how's it easy to compute? Well, say that's the number x. If we compute not x, that's a machine language instruction on most computers, that's just flip all the bits. That's an easy computation. If you take x and you add 1 to x, then all these 1s turn to 0 and we get a 1. So x plus 1, that's also easy to compute. You just increment x. But if you take these two values now and we AND them together bitwise, then since everything to the left, we flipped it and it's different, it's going to come out 0. One's going to be 0, the other's going to be 1. Both of them are the same over here, so what we're going to get is big R of x. So 3 machine instructions on a typical computer is going to give us big R of x. Kind of amazing. But that's a bit-whacking fact. People studied functions like this, and there's 100 pages in Knuth Volume 4 about functions like this. And it's actually also, well, I wouldn't call it easy, maybe in a dozen machine language instructions, you can also compute little r of x on most computers. So we're actually going to just use big R. But the bottom line is we can think of these types of functions as to be things that can be computed with just a few machine instructions. And that was one of our constraints. We wanted to, when we get a data point, we want to be able to handle it with just a few machine instructions. And these are the types of operations that we're going to use. So here's Flageolet and Martin probabilistic counting method. What we're going to do is maintain just a single word that summarizes the whole data stream. And that's called a sketch. And for each entry in the data stream, what we're going to do is compute big R of that entry with those 3 instructions. And then we're going to bitwise OR that into the sketch. And then at the end, after we've processed them all, we're going to use the position of the rightmost 0 in the sketch to estimate log base 2 of n. So here's what it looks like, just a typical one step in the algorithm. After a while, this is after running it for like a million things. That's what it might look like. So we get a new entry, say it's this entry here that we were using. Its big R value has just this 1, 1 where the rightmost 0 was. And we're going to OR that into the sketch. Well, since the sketch already has a 1 in that position, it doesn't change the sketch. And you think about it for a while, this thing is going to be 2 to the k with probability about 1 over 2 to the k. That you need that many zeros and a 1 for this thing to be 2 to the k. That's the number of trailing 1s. So if you think about it a little more, it means that after we've seen a lot of data, the leading bits are going to be almost surely 0. Very unlikely that we'll get an entry in our random data stream that has all zeros with a lot of 1s with a 0 way over to the left. On the other hand, the trailing bits are almost surely 1. Very likely that we'll get one that has a 1 at the rightmost and so forth. And then in between, there's going to be some bits that might be 0 or 1. And what Flageolet and Martin decided was what we're going to do is just take that position of the rightmost 0 to be a rough estimate of what log n should be. Again, just following from the 1 over 2 to the k probability. And then a rough estimate of n is take big R of the sketch. So to get n, so now we do the whole algorithm with big R. This is a very simple algorithm. There is going to have to be a correction factor, and we'll talk about that in a minute. That has to do with the analysis. This is just a trace for certain values that we can run through to just check understanding of the algorithm. So we start out, the sketch is all zeros. We get that value. Its big R is 1, 0, 0, so we get a 1 in the sketch. Our next one, the rightmost 0 is in position 1. The big R value is that, so we get a 1 in that position of the sketch. Next one is the same as the first one. Sketch doesn't change. Next one is position rightmost 0 is 5, so we get a 1 in position 5. Next one, the rightmost 0 is at the end, so we get a 1 in the sketch. Then we get another one in position 1, doesn't change the sketch. Another rightmost one, doesn't change the sketch. Most operations are like this, little action over on the right. But remember, it's only taking us a few operations to compute big R, no matter what its value is. Okay, now we get a 3, so now we fill in another bit there. Now we get a 6, so now way over in position 6. And then a little action. So even for this small entry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries, we get an estimate for the number that we've seen of 16, and it was 10, actually pretty close. The big R of this value is 1, all zeros. That's a trace of probabilistic counting. And this is the code. It's an extremely simple algorithm. Big R is just not x ANDed with x, bitwise ANDed with x plus 1. If we have a stream, we have our sketch. It's initialized to 0. For every entry in the stream, we replace the sketch by sketch or big R of the hash value of s, and then return R. This is, okay, there we are, single word, or all values of R of x in the stream, return the smallest value not seen. So this is a really early example of what we used to call a simple algorithm whose analysis isn't. It's a 4-line algorithm, actually 3-line algorithm was a declaration. The algorithm was invented by a database researcher at IBM, and he just ran this on lots of examples. And what he found was the estimate was consistently a little bit low, and he wanted to know how much. And Flageolet was visiting at the time. But first, what Martin did was just empirically obtain the correction factor. Just run it on a lot of examples and then come up with a correction factor. It's one way to go, but it doesn't really derive from an understanding of what's going on. And what Flageolet said is you really have to do the math. And if you do the math, you find out that the correction factor needs to be 0.77351. And if you don't have that math and that hypothesis and that validation, it's not really an algorithm. So here's the mathematical analysis of probabilistic counting, the theorem that Flageolet proved. It says that the expected number of trailing ones in the sketch in this process is log base 2 of phi n plus p of log n, where that's an oscillating function of very small amplitude, actually less than 10 to the minus 6, where this factor phi is 0.77351. Now, I'm not going to give the proof in this lecture. In the 1980s, there were only a few people in the world who might have attempted such a proof, and that's Flageolet. By the 1990s, it was understood that this is a parameter in a data structure called a trie, which you might have encountered if you've studied algorithms. This is a structure built from a binary stream where you go left of 0 and right of 1, and it's the highest null node left of the right spine. And so understanding it from that point of view, that's kind of equivalent to the trailing ones in the sketch. And nowadays that's considered standard analytic combinatorics. And eventually we'll get to an understanding of proofs of results like this. So these are references of modern proofs that show that in the code that our sketch divided by 0.7731 is an unbiased statistical estimator of n. And there's also possible to get the variance in other moments. In other words, our hypothesis is that the expected value that we get from probabilistic counting is going to be n for random values from a large range. So here's an example with 20 trials. There's 100,000, 31 random bit values, 20 trials. There's 100,000, and it's close. Now, if you look for a minute, you might notice something about these values. And Flageolet and Martin said right away that typically the result is one binary order of magnitude off. That's within a factor of 2. And yeah, it's kind of that way. But when you think about it, of course it is, because it always returns a big R value, which is a power of 2, divided by 0.77351. So that means there's only a few different values that you could get. So for example, if it turns out to be 16384 divided by 0.77351, you get the value 21,181, and we got that. Or you might get twice that, or 4 times that, and so forth. These are the only possible values that we could get. So it's not surprising that you're not going to hit it exactly. If your value of n is a power of 2, fine, you'll hit it exactly a lot of times, but you'll still be off by a power of 2 the other times. And thinking about this, it's not hard to see that what we want to do is somehow incorporate more experiments into the process to get more accuracy. And that's the next part of the story.